Okay, I am Chih-Mao Chen from LLD Technology, and today I'd like to give short introduction to Linkerization in LLD. So we at LLD are a founding member of the RISC-V Foundation, and also a contributor to the RISC-V open source ecosystem. We have been working on RISC-V support in the LLVM linker, including Relaxation, for a number of years, and we'd like to share what we have done, and also contribute our work back to the open source community. So first, what's linker Relaxation? To illustrate that, we will start with an example here. This is a C code where we define a main function, and inside this main function, we call another function foo. This foo function is defined externally outside of this file, so we cannot see its definition. Next, what happens if we ask compile to compile this file? We know that the compile has to generate some code to invoke this foo function, but it does not know where this function will be placed eventually. So to be safe, the compile has to generate code with a large possible range here with an AYP instruction and also a JLI instruction. It also takes a RISC-V code location on the instruction here to tell the linker that issue the locator PGFT offset to foo here at link time. Okay, then as we try to link this object file with foo defined in maybe another object file. The linker lays out the functions and computes the PGFT offset and rewrites this code function and this code instruction relocation. So so far so good, right? But we can also see that this offset here is actually only like 100 bytes apart, and this is actually well within the range of RISC-V jump and link instruction. So an optimized linker should be able to rewrite this code sequence to a single JL, right? This will save one instruction and also 4 bytes here. So this optimization to rewrite code sequence with shorter and more efficient ones is called Linkerization. Okay, so the case of Linkerization is that from compiler's view, it only works on one translation unit at a time. So it has no information about the final layout of the functions and data and in the executable. So therefore, it has to assume the worst case by generating the most conservative functions. And it can also emit a registration hint to tell the linker that it's possible to rewrite the code sequence with a shorter one. And then from the linker's point of view, the linker has global information about the address of all functions and symbols. So to perform relaxation, it simply has to check each relaxation hint and also determines if it's possible to replace the code sequence with a shorter one. So now you may ask here what kinds of relaxation in RISC-V are possible. The answer is that there are many, but we will only look at the 2 types of relaxation below. So the first kind of relaxation is called code relaxation. So the compiler uses the call pseudo instruction or tail pseudo instruction to call or tail call a faraway subroutine. This pseudo instruction is expanded to a pair of AYPC and the JLI instruction. And this can address about 2 gigabytes in each direction, but this takes 8 bytes of space. If the jump range is within 1 megabyte, we can relax the code sequence to a single jumper link, which saves us 4 bytes here. And then if the compressed extension is available, we can further raise this to the compressed jumper link or the compressed unconditional jump. This tool only takes 2 bytes, so this is a 6 byte saving over the original form. The other kind of relaxation is the GP relative relaxation. In RISC-V, the API defines the X3 register as a dedicated global pointer register, which is called the GP. The value of this register is initialized to the symbol underscore global pointer $ at the start, and this value remains unchanged during execution. And this symbol is typically assigned to the session as data plus 2 kilobytes here, which means that small data placed in the data session can be addressed by GP as its base register plus 2 kilobyte of sum. So here we have another example to load data from the symbol thing here using the loop instruction and the 12-bit displacement in the immediate of the lower instruction. So if this thing symbol is a small data, and at the link time we assign the symbol to an address that is within the 2 kilobyte range of GP. We can change here the lower instruction to use GP as the base register and put the GP relative offset into the intermediate. So now, since the address of the foo is formed by the lower instruction itself, this loop instruction is now redundant and can be safely deleted. So this is with a single instruction and also 4 bytes of savings. So for now, we have described 2 kinds of relaxation in RISC-V, but relaxation also introduces a new issue regarding to the alignment handling. So we will walk through this with another example here. This is the previous code, so we know that the first 2 instructions here may be related. And these 2 instructions are followed by an alignment directive here that says the next instruction at I should be A by aligned. So when we assemble this into the second code fragment here, the assembler sees that this at I here is already A by aligned, so it does not try to insert paddings to make this at I aligned. Then the problem now comes when the linker tries to relax the first 2 instructions into a single instruction. And then now you can see here, this add-I instruction is no longer A by aligned. And for now, the linker actually has no way to know that this code is aligned, and it has no way to fix this. So to make alignment work, in code compiled with relaxation enabled, each alignment directive is padded with the worst possible bytes of knobs. So in this case, this is 6 bytes of knobs here, and these knobs are also tagged with an alignment relocation here. Then at the link time, the linker proceed to perform relaxation as usual. So you relax these 2 instructions into a single one. Then it has to process the this alignment relocation. So it is that the next add-I instruction has to be A by aligned, so it has to leave us 4 byte knob here to keep this add-I aligned. So it deletes the extra 2 byte compressed knob here to keep this add-I aligned. But this has a very serious implication. So any object files compiled with relaxation enabled cannot be linked by linkers that do not support relaxation. Since you can see, these objects are naturally unaligned, and it's now the linker's responsibility to handle the alignment. Okay, so back on LLD, the LLVM linker. LLD is a sub-project in LLVM, and it is a drop-in replacement for the glue linker. It's designed to be very fast, and like LLVM, it has a permissive license, and it is also an embeddable architecture, and by default also a cross-target linker. So being a cross-target linker, RISC-V is also among the architectures supported by LLD. Back in 2017, we first contribute a patch to support basic RISC-V relocation to LLD. And since then, many people have also contributed to the RISC-V port in LLD so far. However, linkerization is still not supported by LLD yet. And unfortunately, this means that LLD cannot be used to link the majority of RISC-V libraries due to the missing alignment handling. So this has seriously limited the usefulness of LLD in RISC-V software ecosystem. So in April this year, we post a proof of concept patch for review that fully implements all kinds of relaxation in RISC-V, as well as alignment handling. Right now, this is under early review, and we are looking for comments and feedbacks for this patch. And in the following sessions, we will briefly discuss what this patch does. So to start, we will take a very high-level overview of how LLD works. So first, it has to pass the input files and add the symbols into the symbol table, and then also resolves any undefined symbols in these files. Next, it has to scan relocations in each session to determine if it needs to generate some things like a global offset table or dynamic relocations. It then lays out the sessions and the computer address of each symbol, and then performs relocations on each session based on this layout. Finally, writes out the link executable to the up file. So to add the relaxation support in LLD, it needs to work on temporary assigned symbol addresses. So it seems most natural to add the relaxation path after session have been laid out, but before the session contents are relocated. So we add the relaxation path here. And the first problem we encounter when adding relaxation support to LLD is that obviously it needs to modify the input sessions, including the session content and the symbols and the locations. So we have to add some infrastructure to support these operations. In LLD, the input sessions are memory mapped from the input files. So we have to add a mutable data function to make a writable copy of the content. And the next thing is that we have to add a function that takes a vector of ranges we have to delete in a relaxation path. This moves the session content and also adjusts the symbols and locations, and then reduce the size of the session. And in the implementation, we also presolve the offsets to ensure that the deletion works in linear time. Okay, so to perform relaxation, we simply check for each input session which is executable, and within those sessions we search for the relax hint. So in RISC-V, the relax hint is inserting the right after the location that it applies to. So we look at the previous location and see if the location can be rested. We also need to keep a mapping where instructions need to be deleted and then remove of them in a single pass at the end of the recession. So let's see how and when we can relax each location. To relax a code location, we have to compute the offset between the caller and the callee. But since each relaxation may further shrink the taxation, this offset may actually become may be changed after each pass. So we have to make some assumptions about this offset, which in this case we assume that the taxations are tightly packed, so the offset can only become smaller after each pass. In addition, we also have to account for the worst case session alignment, because this session alignment may enlarge the offset between the caller and callee. Then we use this worst case offset to determine what kind of jump instruction we can convert the code into. So this may be a jump link over the corresponding complex instructions. Then for the high 20 and the low 12 locations, we only release references to data by converting them to GP relative addressing. So for this to work, this needs to get the address of the global symbol global pointer symbol, and then compute the offset between the symbol and the GP. Here we assume that after each recession pass, the GP relative offset does not change. Since recession only changes the code sections and do not affect the data sections. So if converting to GP relative addressing is possible, we change the S1 in the low 20s to GP, and also delete the corresponding rule. Then for PC relative high 20 and low 12, we also only release references to data by converting them to GP relative. So they are actually very similar to the previous upside versions. However, in RISC-V, the picture below 12 is linked to the picture high 20. So we have to split the recession into two passes. The first pass is releases the low 20s, and then the second pass deals with the high 20s. This makes sure that we don't release the high 20 first, and then causes the lookup from low 12 to high 20 to fail. So recession is an iterative process. Since each after one pass of recession, it can reduce the code size, and this may enable further recessions to occur. So the linker will iteratively perform relaxation until no more changes can be made. This is guaranteed to converge since recession only works in one way by shortening the code sequences. And finally, after all recessions are done, we have close to the final layout of the executable. And at this point, we can start handling the align hints. This is pretty straightforward process. Since each alignment point is already padded by the maximum possible of knobs. So the linker only has to determine how many bytes of knobs it needs to delete. One thing to know here is that the alignment process must always be performed even if relaxation is disabled by the no rest option. This is to ensure the correctness of the alignment. Okay, so to verify the effectiveness of relaxation, we run the relaxation enabled LLD and also the GNU linkers on a couple of benchmarks. So this is the code size reduction of the computer's benchmark game, and also the sure benchmark from both linkers. The baseline here is the original LD with relaxation disabled. So as you can see here, the recession implementation of LD is as effective as the GNU linker. And the geometry mean here, in the geometry mean here, it can reduce about 3.2% of the execute row size compared to LD without linker recession. Okay, for conclusion, so we have presented the implementation of linker recession in LD, and now we hope to hear more reviews and feedbacks on the design and the implementation. And for future work, for now, we have to work on making emitting relocations to work with Relax, and also implement the 3 local storage realizations. So in the end, we hope to make LD a production quality linker for RISC-V, where it will be used by many projects. Okay, thank you very much.